So in our last section of this semester, we're going to take a look at some of the ways that we can begin to apply integrals. And so we'll start here by taking a look at the very important theorem, the net change theorem. Ultimately, what it states is that when I'm integrating something, if the function that I'm integrating is representative of a rate of change, then when I integrate that over some interval a to b, what I actually end up calculating with my fundamental theorem of calculus here is a net change in the overall quantity. So as a quick example, let's suppose that I integrate a function, say capital F prime, but that function measures the amount of volume per second may be acquired in, I don't know, I'm blowing up a balloon, right? And I want to know, like, hey, the volume is changing every second at this rate. Well, then if I integrate over some period of time, that is from some time a to b, then what I'll end up calculating at the end is a total change in the amount of volume. Or maybe I integrate a function, capital F prime, that represents the tons of pollution produced an hour, maybe by a factory. And when I integrate this, what I'm going to end up with is a total amount of change in the tons of pollution that are produced. Or if I integrate velocity, which remember is a rate of change of position, then what I'll ultimately calculate is a change in the position of an item. So we can see that, again, what's really valuable about this is that I can start to actually see that if I understand or if I have different rates, I can actually use them to calculate total changes in a quantity. So let's take a look here at something like example number 1 and try to get a sense of how exactly we can go ahead and plan to use this. So suppose that oil starts leaking from a tank at a rate of 100 minus 5t gallons per minute. Okay, so I'm imagining, I kind of have some sort of a tank sitting here like this, right? Maybe some sort of a hole or something like that appears, and I just start getting stuff, that's pouring out of it. So here it's green. I have some toxic sludge, it's starting to pool over here on the ground, and I'm curious if it's coming out at a speed of 100 minus 5t gallons per minute, where t represents the time from when it starts leaking, then what does this integral represent? Because I'm noticing first here that I'm going to be integrating the speed at which the liquid is leaving the tank, right? It's coming out at some number of gallons per minute. And so, well, if I'm integrating this rate, and then I'm integrating over the interval from 0 to 120, which should be represented by my value of t, then I should be able to see that this integral here represents the following. This integral represents the total number of gallons leaked from the tank within the first 2 hours. And I'm getting 2 hours here because I'll notice that if I go from 0 minutes to 120 minutes, well, 120 minutes is 2 hours. So notice that this is what I'm calculating. This is how quickly the liquid leaves. Then what I'm calculating is how much total liquid has left. Now, if I take a look at part B, if I was asked to find this total number of gallons leaked in the first half hour, I could think about setting up an appropriate integral to do so. The first thing I would do is, of course, integrate the rate at which this liquid is leaving the tank. And if I only want to go over the first half hour, that would be from 0 minutes to 30 minutes. And of course, then integrating this is no big deal. I have a nice continuous function here. I have a polynomial, so I can use my fundamental theorem of calculus part 2. So my antiderivative here should be 100t minus 5 halves t squared. And then I'm just going to evaluate this from 0 to 30. So let's see, if I plug in 30 here, I'm going to get, it's going to be, 3,000 minus 5 halves, 30 squared, that's going to be 900. So I'm going to end up with, let's see here. So this is going to be let's see, 9 times the 5, it's going to be 4,500 chopped in half. So this is going to be 3,000 minus 2,250. So that's 750 gallons. That's how much has left this tank in the first 30 minutes. I found this total amount of change. So this is a really, again, cool idea that we can take these rates and actually integrate them to try to go ahead and figure out total changes. Now, one thing to be aware of here is that this formula that I have for the rate of the change in the gallons that are leaving the tank is completely ridiculous. There's no way that this would actually model the rate at which liquid was leaving the tank, but I wanted to come up with an easy example. One of the reasons that you could tell that this is pretty ridiculous is that you can see again the speed at which the liquid is leaving the tank at any given time. So notice at time 0, the liquid would be leaving the tank at 100 gallons per minute, and it seems to be slowing down. If I was at, say, time 2, I'm down to 90 gallons per minute. But you can see that by the time I'm at time 20, so at the 20-minute mark, I'm going to be at 0 gallons per minute leaving the tank. And once I get to like anything past 20, I'm actually going to have a negative gallons per minute, which means that the liquid will be picking up off the floor and jumping back into the tank. So obviously this is a completely ridiculous rate, but if such a scenario was possible, then of course all of these calculations here would make perfect sense. So the hardest part then, if I was actually going to be applying a question like this to the real world, is I actually have to understand how to calculate or how to find a rate like this. Now, we're not going to take a look at that sort of task here, at least in this section. We're just going to focus again on how do I set up these integrals and how do I kind of interpret the meaning of what they would represent.